Geometric Interpretation of Solutions. Welcome, everyone. Before we dive into today's new material, let's take a moment to reflect on what we have already covered. In our previous lesson, we focused on the algebraic side of things, specifically learning how to classify pairs of linear equations as either consistent or inconsistent based on their coefficients. Now, we are going to take that knowledge a step further. Instead of just looking at numbers and symbols, we are going to explore the geometric meaning behind these terms. Essentially, we are going to see what these different classifications actually look like when we plot them on a coordinate plane. Graphical representation of linear equations. First, remember that when we take a linear equation in two variables, for example, a1x plus b1y plus c1 equals 0, and we represent it on a coordinate plane, it always forms a straight line. Next, we need to define what a solution actually is in this context. If we are looking at just a single equation, a solution is simply any point, which we denote as x and y, that sits directly on that line. This brings us to the core of our topic, a pair of equations. If we are looking for a solution to a pair of linear equations, we aren't just looking for any point on one line. We are looking for a specific point, x and y, that lies on both lines at the exact same time. As we will see in the next slide, this shared point is what we call the intersection, and there are three different ways these lines can relate to one another. Now that we've established that we are moving from classifying equations to understanding their geometric meaning, let's look at how these equations actually appear on a graph. Intersection of lines. Now that we understand that a solution to a pair of equations must be a point that lies on both lines simultaneously, let's look at what this looks like visually. Geometrically speaking, finding that solution simply means finding the exact point where the two lines intersect or cross each other. However, it is important to realize that lines don't always cross in the same way. Depending on how these lines are positioned relative to each other on the coordinate plane, we are going to encounter three distinct possible scenarios. We will examine each of these, intersecting, parallel, and coincident lines, one by one in the next few slides. 1. Intersecting lines. Now that we understand that a solution is essentially a shared point between two lines, let's look at our first scenario, intersecting lines. Imagine you are drawing two lines on a coordinate plane, and as you extend them, they cross each other at exactly one single point. When this happens, we call these intersecting lines. If we look closely at the geometric observation here, you'll notice that the lines meet at a single, unique point. Because this specific point is the only place where the two lines occupy the same space, it represents our solution. Therefore, in terms of the number of solutions, since there is only one common point, we say the system has a unique solution. Finally, because a solution does exist, even if it's just one, we classify this pair of equations as a consistent pair. We'll see how this compares to the next case, where the lines never meet at all, in just a moment. Real-world example, a road junction. Now that we understand the theory behind intersecting lines, let's bring this concept to life with a real-world example. Imagine you are looking down at a map of a small town. You see two straight roads, let's call them Road A and Road B, that cross each other at exactly one intersection point. To turn this into a math problem, we can follow three simple steps. First, we represent Road A as a linear equation. Second, we represent Road B as another separate linear equation. Now, think about the junction where these two roads meet. That specific location, the junction itself, is the only point on the map that belongs to both Road A and Road B at the same time. Therefore, we can conclude that this intersection represents a unique solution. This perfectly illustrates the intersecting lines scenario we discussed in the previous slide, where there is exactly one common point between the two lines. 2. Parallel lines. Now, let's move on to our second scenario, which is the case of parallel lines. Think about two lines that are positioned such that they are always the same distance apart. No matter how far you extend these lines in either direction, even if they went on forever across the coordinate plane, they would never, ever meet. If we look at this from a geometric observation standpoint, the key takeaway is that these lines never intersect. There is no crossing point. Because of this, when we talk about the number of solutions, we find that there are no common points shared between the two lines. Since a solution is defined as a point that lies on both lines simultaneously, the system, in this case, has no solution. Finally, because there is no point of intersection to be found, we classify this pair of equations as an inconsistent pair. To help you visualize this concept more clearly, let's look at a real-world example involving railway tracks on the next slide. Real-world example, railway tracks. Now, to help you visualize the concept of parallel lines that we just discussed on the previous slide, let's look at a real-world example, railway tracks. Think about the two metal rails of a straight railway track running alongside each other. In step 1, we can represent the left rail as a single linear equation. In step 2, we represent the right rail as a second, separate linear equation. Now, here is the crucial part in step 3. For a train to run safely, these two rails must always remain exactly the same distance apart. This means they stay equidistant, and no matter how far the tracks extend, they will never cross or touch each other. So, to reach our conclusion, because these two lines, or rails, never intersect, there is no common point shared between them. In mathematical terms, this means the system has no solution, which, as we will see in the next slide, is the defining characteristic of an inconsistent pair of lines. 3. Coincident lines. Now, we have looked at what happens when lines cross and what happens when they never meet. But there is a third, and perhaps most interesting, scenario: coincident lines. Sometimes you might encounter two different-looking algebraic equations that, upon closer inspection, actually represent the exact same line. When you go to plot these on a coordinate plane, you won't see two separate paths. Instead, one line lies directly on top of the other. If we look at our geometric observation here, the key takeaway is that the two lines overlap completely. They are essentially identical. Because they are overlapping, think about what this means for our solutions. Unlike the intersecting lines we discussed earlier, which only share one single point, or the parallel lines which share none, these lines share every single point along their entire length. Since every point on the line satisfies both equations, we say the system has infinitely many solutions. Finally, let's look at how we classify this. Because a solution does exist, we still call this a consistent pair. However, because one equation is essentially a duplicate of the other, we specifically refer to this as a dependent pair. This sets the stage for our next slide, where I'll show you a real-world way to visualize this overlapping effect. Real-world example: overlapping paths. Imagine two people, person A and person B, are both describing the exact same path they take from home to school. In step 1, we plot the path described by person A on our coordinate plane as a straight line. In step 2, we plot the path described by person B. Now, in step 3, you will notice something very specific. Because they are describing the same route, the second path lies exactly on top of the first path. They are perfectly overlapping. From this, we reach our conclusion. Since the lines are overlapping, every single point along this path is a common point for both descriptions. Therefore, we have infinitely many solutions. This is the perfect real-world representation of what we call coincident lines, which we will summarize in our final review table in just a moment. Now, let's bring this third scenario to life with a real-world example, similar to how we looked at the road junction and the railway tracks in the previous slides. To visualize this mathematically, let's follow a three-step process. Summary table for quick reference. Now that we have explored each of the three scenarios in detail, looking at road junctions, railway tracks, and overlapping paths, let's bring everything together. I have prepared this summary table to serve as your quick reference guide for exams and revision. let's look at the first row. When we have intersecting lines, the geometric representation shows them meeting at exactly one point. Algebraically, this means there is a single point of intersection, which we call a unique solution. Because a solution does exist, we classify this system as consistent. Moving down to the second row, consider the case of parallel lines. Geometrically, these lines never meet, meaning there is no common point between them. Consequently, there is no solution to the system. Because the lines never touch, we use the term inconsistent to describe this pair. Finally, let's look at the third row, which covers coincident lines. In this case, the lines overlap completely, so every single point on the line is an intersection. This results in infinitely many solutions. Since we do have solutions, this system is still considered consistent, but we specifically call it a dependent pair because one equation depends on the other. Keep this table in mind as we move to our final slide, where I will highlight some key takeaways and common pitfalls to avoid during your calculations. Key takeaways. First and foremost, always remember the fundamental concept. A solution to a pair of linear equations is simply the point of intersection of the two lines. When we talk about a solution, we are looking for that specific coordinate where the two paths meet. First, we have intersecting lines. As we saw with our road junction example, these lines cross at exactly one point. This leads to exactly one solution, and because a solution exists, we classify this system as consistent. Second, we have parallel lines. Think back to the railway tracks we discussed. These lines never meet, meaning there are zero solutions. Because there is no point of intersection, we call this an inconsistent pair. Finally, we have coincident lines. This is the case where the lines overlap completely, as in our overlapping paths example. Since they occupy the same space, every point on the line is a shared point, giving us infinity solutions. Because solutions do exist here, this system is also considered consistent, specifically a dependent pair. All right, class, we have covered a lot of ground today, so let's bring everything together with this final summary of our key takeaways. To make this easy to memorize, let's look at our 3 specific scenarios. Keep this summary in mind as we move into our next session, where we will learn how to identify these 3 cases using only the algebraic coefficients of the equations. Common mistakes to avoid. First, a very important distinction. Do not confuse no solution with zero. I often see students see the term no solution and mistakenly assume that the answer is simply x equals 0 and y equals 0. That is not the case. As we discussed with the parallel railway tracks in our earlier example, no solution means that there is no pair of numbers, x and y, that can satisfy both equations at the same time. There is no point of intersection at all. Second, be careful not to misidentify coincident lines. When you are looking at a graph, it is easy to mistake coincident lines for parallel lines because, in both cases, you don't see that classic X shape where the lines cross. However, remember the key difference. Parallel lines are 2 separate lines that never touch, whereas coincident lines are actually the exact same line, lying directly on top of one another. Finally, let's clarify the confusion regarding consistency. It is easy to get lost in the terminology, but just remember this simple rule. Consistent simply means that at least one solution exists. This is why, as we noted in our summary table, both intersecting lines, which have one unique solution, and coincident lines, which have infinitely many solutions, are both classified as consistent. Now, before we wrap up today's lesson, I want to pause and address some common pitfalls. As we've seen throughout this session, moving from algebra to geometry can sometimes lead to a few misunderstood errors, so let's clear these up. Keep these distinctions in mind, and you'll have a much stronger grasp of the geometric interpretation of these systems.